buffer solution is one of the most important topics of Ionic Equilibria. So a buffer is a solution which maintains its pH around some constant value even if a strong acid or a strong alkali is added into it, a small amount of a strong acid or strong alkali. So there are two types of buffers, acid buffers and alkaline buffers. The main in our syllabus mainly there's acid buffers. So to form an acid buffer, what is needed is a weak acid and the salt of the weak acid. For example, if there is ethanoic acid, then the salt of ethanoic acid, that is sodium ethanoate, will be required. So 50 centimeter cube of 0.1 molar ethanoic acid and sodium ethanoate is taken. The sodium ethanoate dissociates irreversibly into ethanoate ions and sodium ions. Ethanoic acid dissociates reversibly into ethanoate ions and hydrogen ions. Right? Now let's say that a small amount of a strong acid, for example HCl, is added. So what happens is that the concentration of hydrogen ions increases, which is why the pH value decreases. However, as the concentration of hydrogen ions is increasing, so it reacts with the ethanoate ions, forming ethanoic acid, which is why the concentration of hydrogen ions again decreases and pH roughly stays the same. So this is the equation, and for a general case, the equation would be the salt, that is the ethanoate ions, react with the hydrogen ions from the HCl to form the weak acid, that is HA. When a small amount of a strong alkali like NaOH is added, so what happens is that the NaOH provides hydroxide ions. The hydroxide ions react with the hydrogen ions and lower the concentration of hydrogen ions. So the equilibrium shifts towards the right hand side and more hydrogen ions are produced. Right? So basically what happens is that how we write this in an equation is that the ethanoic acid reacts with the hydroxide ions from the NaOH to produce ethanoic acid and water. So I'll show what is happening basically. Just a second. Yeah. So OH negative ions coming from the sodium hydroxide react with the hydrogen ions present to form water. This is why the concentration of hydrogen ions decreases. So this reaction occurs in the forward direction. So CH3 COOH forward reaction, so CH3 COO negative plus H plus. Now if we add the two equations, you will get CH3 COOH plus OH negative. The hydrogens get cancelled, producing CH3 COO negative plus H2O. So that's the general equation. The weak acid reacts with hydroxide ions to produce salt and water. So this was for ethanoic acid and sodium ethanoate. Now other examples can be hydrogen phosphate ion, H2PO4 negative and HPO4 2 negative, right? So over here the acid will be the compound which has more number of hydrogen because it has higher tendency of donating hydrogen. So this is the acid and this is the salt, right? So with acid, when small amount of acid is added, what will be the equation? So the general equation was salt plus hydrogen ions forming the weak acid. So the salt HPO4 2 negative plus hydrogen ions forming the weak acid. With alkali, the general equation is this one: the weak acid plus hydroxide ions produce the salt and water. So this is how it's maintaining the pH, right? What happened in the case of the strong acid was that hydrogen ions increased, so the hydrogen ions reacted with the salt to produce the weak acid. pH increased again, sorry. And in the case of alkali, the hydroxide ions reacted with the hydrogen ions and so the hydrogen ion concentration decreased, which is why the pH increased. So the equilibrium shifted towards the right hand side, more hydrogen ions are formed. Again, pH was lowered and it came back to a constant value. So next example is of HNO2 and NaNO2. Nitric acid is the acid, NaNO2 will be the salt. So with acid, what happens is that the salt reacts with hydrogen ions to give the weak acid. The salt is basically NO2 negative. The ion in the salt plus hydrogen ion gives HNO2. With the alkali, the weak acid reacts with hydroxide ions to produce the salt plus water. In the fourth example, there is HCO3 negative and CO32 negative. This will be the acid because it has more hydrogen. This will be the salt. So when the acid is when a small amount of acid like HCl is added, then the salt reacts with the hydrogen ions from HCl to give the acid, increasing the pH again. And when an alkali is added, so basically the acid reacts with the hydroxide ions from the alkali to give the salt plus water. This lowers the pH back to the constant value. This is an alkaline buffer. In an alkaline buffer, we need a weak base and the salt of the weak base. So an example can be ammonia aqueous and ammonium chloride, which is the salt of ammonia. So ammonium chloride will dissociate into ammonium ions and chloride ions. Ammonia reacts with water because it's aqueous to give ammonium ion and hydroxide ion. Now basically, when a strong acid is added, so the concentration, like HCl is added, the concentration of H plus ions increases. So what happens is that the ammonia reacts with the hydroxide ions react with the hydrogen ions from the acid. The hydroxide ions react with the hydrogen ions to form water. So equilibrium shifts towards the right hand side and ammonium ions are formed, right? So basically hydrogen ions from the acid plus the hydroxide ions in the solution produce water. So equilibrium shifts to the right hand side. So it's NH3 plus H2O produces NH4 plus OH negative. So water and water, OH and OH get cancelled. The overall equation is NH3 plus H plus produces NH4 plus. So this is the overall equation, right? Now when a strong alkali is added, so what happens is that the concentration of OH negative ions increases. So equilibrium shifts towards the left hand side and ammonia and water are formed. This prevents the pH from increasing because the concentration of hydroxide ions again decreases. So this is how an alkaline buffer works. Now an example can be of amino acids. This is a simple amino acid. Now when an acid is added to the amino acid, basically over here an amino acid basically has an alkaline group and an acidic group. So when an acid is added, the concentration of hydrogen ions increases. So the hydrogen ions react with the alkaline part of the amino acid, that is the NH2 part. So nitrogen basically has two lone pairs. So it forms a dative bond with the hydrogen to give NH3 plus. So this prevents the pH from decreasing. When an alkali is added, then the hydroxide ions from the alkali react with the acidic part of the amino acid, that is COOH. The COOH donates its hydrogen to OH negative, forming water, and a salt is formed from the amino acid. So this prevents the pH from decreasing too much. These are the calculations with buffer solutions. These are mainly with acid buffers. So in an acid buffer, in an acid buffer, we have a weak acid and its salt. So basically a weak acid, the dissociation of weak acid is HA dissociating into H plus the salt, right? This is the weak acid, this is the salt. So And we know that the acid dissociation constant is H plus into A negative upon the concentration of H plus into concentration of salt upon concentration of the acid. So I can shift concentration of acid upon concentration of salt onto the other side, apply negative log on both sides. We get negative log of H plus concentration of H plus equals to negative log concentration of HA upon A negative into Ka. So using the log properties of log, negative Lg of concentration of H plus becomes pH. This is negative Lg Ka, which is equals to pKa, and this is negative Lg Ha upon A negative. This can also be written as positive Lg A negative upon Ha. The derivation again is not important. If you're a math student, then you'll understand, or else you can just learn the result. This is the formula that we'll be using mainly. So the question is, a buffer solution is prepared containing 2.35 times 10 power negative 2 moles of methanoic acid and these many moles of sodium methanoate. So methanoic acid is the weak acid, sodium methanoate is the salt of the weak acid. These moles in 1 dm cube. So basically there are 2.35 times 10 power negative 2 moles of methanoic acid in 1 dm cube. So that's basically the concentration of methanoic acid, and this is the concentration of sodium methanoate. Then they're saying the Ka of HCOOH is this much, and calculate the pH of the solution. So part A, the formula for pH is pKa plus log of concentration of salt upon concentration of acid, right? So first we'll find pKa. pKa for pKa is basically negative log Ka, that is equals to negative log 1.78 times 10 power negative 4. So that is equal to 3.75. Now after that we need the concentration of the salt and the concentration of the acid. So basically, as I mentioned earlier, these are actually the concentrations of the acid and the salt because they are the moles in 1 dm cube. So concentration of salt is equals to 1.84 times 10 power negative 2, and the concentration of the acid is equals to 2.35 times 10 power negative 2 molar or mole per dm cube. So pH is equals to 3.75 plus log acid salt concentration, that is 1.84 times 10 power negative 2 upon acid concentration, that is 2.35 times 10 power negative 2. So this will be equal to 3.64. Sorry, I didn't move the page up. So basically what I did was that the salt concentration is the same as the number of moles because it's in 1 dm cube. Same as with the acid concentration. The formula, I then applied the formula of pH. pKa we found as 3.75. Salt concentration was 1.84 times 10 power negative 2, and acid concentration was 2.35 times 10 power negative 2. So that is how we found the pH. Then part B, the question says, if 5 centimeter cube of 0.1 molar HCl is added, calculate pH of the buffer. Right, so 5 cm cube of HCl, 5 cm cube of 0.1 molar HCl is added. So I'll find the moles of HCl first. 5 cm cube and 0.1 molar. So this is coming equal to 5 times 10 power negative 4. Now I'll show the equation that we use for acid buffers when an acid is added. So when an acid is added, the equation is salt plus hydrogen ions producing the weak acid. So what happens over here is that when HCl is added, so the hydrogen ions react with the salt. The salt was sodium methanoate's methanoate ion, that is HCOO negative plus hydrogen ion react together to produce HCOOH. So over here, now we know that the moles of H plus ions are 5 times 10 power negative 4. So basically what I'm doing now is that again I have to find the pH, right? So pH is equals to pKa plus log concentration of salt upon concentration of acid. So pKa I know that is 3.75. Now I have to find the concentration of salt and the concentration of the acid. So for that what I'll do is that I'll find the moles of the salt and the acid after reaction with the hydrogen ions from the HCl. So these are the hydrogen ions from the HCl that reacted with the salt to produce the acid. So I know that the moles of the salt were 1.84 times 10 power negative 2. Moles of the acid were 2.35 times 10 power negative 2. So basically what happens is that the hydrogen ions react with the salt to produce the acid. So hydrogen ions are the limiting reactant over here because they're lesser in number. So this is basically initial state and then the final state. So all of the hydrogen ions will react with the salt, right? So to find the final moles of salt, we'll have to subtract 5 times 10 power negative 4 from 1.84 times 10 power negative 2. This is equals to 0.0179. These are the final moles of the salt. For the acid, so if 5 times 10 power negative 4 moles of H plus react with salt, so 5 times 10 power negative 4 moles of the acid will be formed as the ratio is 1:1. So to find the final moles of the acid, we'll have to add 5 times 10 power negative 4 to the initial moles. This will be equals to 0.024 moles. So now we have the moles of the acid and the salt. pKa was 3.75. Now because the volume of the acid and the salt are equal, so the molar ratio will be the same as the ratio of the concentrations. That's why we can just use the number of moles to find the ratio of the concentrations. So the concentration of salt will be 0.0179 upon the concentration of acid, which will be 0.024. So this gives pH as 3.62. So you can see that there was a very slight change because this was a buffer solution, so it prevented a large change in the pH. So I'll go over the question again. The first part I believe was simple. In the second part, what happened was that 5 cm cube of HCl was added, that was 0.1 molar. So this so I found the moles of HCl, right? And this will be the same as the moles of H plus ions from the HCl because the ratio is 1:1. Basically HCl gives H plus plus Cl negative. So number of moles of HCl and H plus are equal. So that means that 5 times 10 power negative 4 moles of H plus were provided to the solution. These, and as we did earlier, in an acid buffer, when an strong acid is added, the H plus ions from the acid react with the salt to produce the weak acid. So that's the equation. Now the H plus ions will react with the salt. This initial moles of the salt were this, the initial moles of the acid were this. Now because the H plus ions were the limiting reactant, they were lesser in number, so all of them will react, and since the molar ratio is 1:1, so 5 times 10 power negative 4 moles of the salt will also react, so we subtract that from the initial moles to find the final moles. Whereas 5 times 10 power negative 4 moles of this acid will be produced because there is a 1:1 ratio, so we add that to the initial moles. So we've gotten the moles of acid and salt at the end of the reaction. So using the pH formula, it's pKa plus log concentration of acid upon concentration of salt upon concentration of acid. Basically, because the volume is the same, so the ratio of the moles will be the same as the ratio of the concentrations. So I just used the ratio of the moles, that is 0.0179 upon 0.024, and I found the pH. And you can see there is a very slight difference, which means that this was a buffer solution. So next question. When chlorine dissolves in water, the following reaction occurs. When a solution of chlorine is used for water purification, the pH of the solution is kept near to pH 7 by addition of a base. Chlorine is dissolved in water to produce 1000 cm cube of solution containing 0.17 moles of HClO and 0.17 moles of HCl. A buffer solution is then prepared by adding 0.2 moles of NaOH. The NaOH initially reacts with HCl. Calculate the pH of this buffer solution. So buffer solution is basically formed by a weak acid and its salt. So when chlorine is added to water, there are two acids formed, HClO and HCl. HClO is the weak acid, right? So we have to find basically pH of the buffer solution, that is equals to again pKa plus log concentration of salt upon concentration of acid. So pKa I'll find first. pKa we know will be equal to negative log of Ka. So Ka is given as 2.9 times 10 power negative 8. This is coming equal to 7.54. So we have the value of pKa. Now we need the concentration of salt and the concentration of acid to find the pH. So the salt, what is the salt and what is the acid? The acid is basically HClO and the salt is basically ClO negative. What's happening over here is that chlorine was dissolved in water, so this reaction has occurred and these many moles of HCl and these many moles of HClO are present in the solution in 1000 cm cube, right? Since 1000 cm cube is equal to 1 dm cube, so we can say that 0.17 and 0.17 are basically the concentrations of the two acids in mole per dm cube. Okay, so now what they're saying is that HClO and HCl is present and then NaOH is added 0.2 moles and it reacts first with HCl. So NaOH is added, it reacts with HCl to produce NaCl obviously plus H2O. So the initial moles of NaOH are given as 0.2. Initial moles of HCl are 0.17. These are the initial moles. And NaCl and H2O are 0. The final moles will be, so over here HCl is the limiting reactant, so all of it will be used. So because it's a 1:1 ratio, so 0.17 moles of NaCl will be produced and 0.17 moles of H2O will be produced. And 0.17 moles of NaOH will be used up, so that means that 0.03 moles of NaOH remain, right? Now NaOH has reacted with all of the HCl. Now it will react with HClO, NaOH, sorry. So it will produce NaClO plus H2O. Now again over here, HClO has there are 0.17 moles of HClO, 0.03 moles of NaOH, 0 and 0 for NaClO and H2O in this reaction for now. Now NaOH is the limiting reactant, so all of it will be used. There is a 1:1 ratio, so 0.03 moles of NaClO and 0.03 moles of H2O will be produced. And HClO, 0.03 moles of HClO will be used, so 0.17 minus 0.03 is equals to 0.14, I believe, right? So we have the final, again these were the initial and the final. So we have the final moles of the weak acid and the salt. The salt is ClO negative, and because NaClO produces Na plus ClO negative, so the ratio is 1:1, so that's why the moles of ClO negative will also be 0.03. So pH is equals to pKa, which is 7.54, plus log of concentration of salt upon concentration of acid. Again, the volume of the acid and salt is the same because it's one mixture, so their ratio of moles will be the same as the ratio of the concentrations. So I'll take the ratio of the moles. Salt upon acid. Salt is 0.03, acid is 0.14. So this is coming equal to 6.87. I hope the question is clear. So the numerical value for Ka for NH4 plus ammonium ion is given. A buffer solution was prepared by adding 0.8 dm cube of 0.25 molar NH3 and excess to 0.2 dm cube of 0.2 molar HCl. Calculate pH of the buffer at 298 Kelvin. So basically, I'll use the formula for pH, pKa plus log concentration of salt upon concentration of acid. pKa is equals to negative log of Ka. This is equals to 9.25. So we have pKa. Now we need concentration of salt and the concentration of acid. So now the buffer solution will basically had NH3 and HCl. So there will be a reaction between NH3 and HCl. Obviously, NH3 plus HCl produces NH4Cl, right? So now I'll find the moles of NH3. Moles of NH3 would be, we have the concentration and the volume. So 0.25 times 0.8, because the volume is in dm cube. So that is 0.25 times 0.8 is 0.2. And the moles of HCl, 0.2 into 0.2 is to 0.04. So the initial moles of NH3 are 0.2, initial moles of HCl are 0.04. This is initial, final, and NH4Cl are 0. So over here the limiting reactant is HCl, so all of it will be used. 0.04 moles of NH4Cl will be made because there is a 1:1 ratio, and 0.04 moles of NH3 will be used. So we'll subtract that to get 0.16. Right, so basically over here the NH4 ions, basically NH4Cl, if we take NH4Cl, it dissociates into NH4 plus Cl negative. So NH4 plus is the acid and its number of moles is 0.04 at the end of the reaction, and its salt will basically be when it loses a hydrogen. So the salt will be NH3 and the number of moles of NH3 are 0.16 at the end of the reaction. I hope it's clear. We have the moles of the salt and the moles of the acid. Now again the formula, pKa we found as 9.25 plus Lg. Again, because the volume is the same for both the acid and the salt as it's one solution, so the ratio of the moles will be the same as the ratio of the concentrations. So that's why I'll take the ratio of the moles. Salt upon acid, salt is 0.16 upon 0.04. This is equals to 9.85. I hope. The next question is, bromic acid is a weak acid. Its Ka is given. Calculate pH of 0.2 mole per dm cube HOBr. Okay, so over here this question isn't really about buffer solutions. It's basic. It's a basic pH calculation question. So for the first part, we'll use the formula pH is equals to negative log root of Ka times acid concentration. So pH is equals to negative log Ka is given as 2 times 10 power negative 9, and the acid concentration is 0.2 mole per dm cube. So from this we can get the pH as 4.7. Second part, 5 centimeter cube of 0.2 molar potassium hydroxide is added to 20 centimeter cube of 0.2 molar HOBr. Calculate the pH of the buffer produced. Right. So again, now we'll have to use the pH formula, pKa plus Lg's concentration of salt upon concentration of acid. pKa we can find easily. It's negative log 2 times 10 power negative 9. This is equal to 8.7. Now there's basically HOBr and KOH. So KOH reacts with HOBr producing KOBr plus H2O. Right, now potassium ions are spectator ions. I'll be removing those. So OH negative plus HOBr. This is OBr negative plus H2O. Now we'll find the number of moles of OH negative ions. That will be equal to the moles of potassium hydroxide. So moles of potassium hydroxide is equals to 5 into 0.2 upon 1000. One times 10 power negative 3. So this is the same as the moles of OH negative. Initial, this is initial moles. Now the moles of HOBr. So in HOBr there is 20 centimeter cube and 0.2 molar. So 20 times 0.2 upon 1000. This is equal to 4 times 10 power negative 3. So 4 times 10 power negative 3. 0 and 0. Right. Now after the reaction, because OH negative ions are the limiting reactants, so all of them will be used. So 1 times 10 power negative 3 moles of OBr negative and 1 times 10 power negative 3 moles of water will be produced. We'll subtract 1 times 10 power negative 3 from the moles of HOBr, so we'll get 3 times 10 power negative 3. So HOBr was the acid, OBr negative was the salt. So we have the moles of the acid and the salt, and the ratio of the moles will be the same as the ratio of the concentrations, because the volume is the same, they're in the same mixture. So pH is equals to pKa we found as 8.7 plus log of 1 times 10 power negative 3 upon 3 times 10 power negative 3. So pH is equals to 8.22. I hope this is clear. Next question is 0.1 molar benzoic acid and 0.15 molar sodium benzoate are mixed. Ka of benzoic acid is given. Calculate the pH of the mixture. Okay, so 0.1 molar benzoic acid and 0.15 molar. This is pretty simple. We basically have to use the pH formula. It's pKa. pKa is basically negative log of Ka plus log concentration of acid, that is 0.15. We'll use the molar ratio because again it is the same mixture, so the same volume. 0.15 for the salt and 0.1 for the acid. So we'll get the pH directly. This was pretty simple. 5.98. I hope these questions were clear, and they are very important because buffer solutions are usually tested. The part for buffer solutions is its uses in the human body. So in the human body, buffer solutions are used in the blood to maintain the pH. So basically cells in the body produce carbon dioxide, So carbon dioxide, so there is an equilibrium established of carbon dioxide and water reacting together to produce hydrogen ions and hydrogen carbonate ions. This is, bio students would know, this is catalyzed by the enzyme carbonic anhydrase, I think. So now over here, if the hydrogen ion, basically if the pH increases, hydrogen ion concentration increases, so equilibrium shifts towards the right hand side, right? And carbon dioxide and water are produced. So hydrogen ion concentration again decreases because equilibrium is towards the left hand side, and pH again increases back to normal. If hydrogen ion concentration decreases, so that means that the pH is increasing. However, equilibrium shifts towards the right hand side and more hydrogen ions are formed, which is why hydrogen ion concentration increases again and pH decreases back to normal. I hope that's clear.